My name is Jaakko Juntunen from Optenni Limited. I will give a demonstration on small loop antenna matching for minimum sensitivity to environment. Printed loop antennas are very inexpensive and can easily be made conformal to printed circuit board in typically for like a wireless car keys. And a typical frequency range in which these antennas are operating is the 433 MHz band. And due to the spatial constraints, a typical loop diameter is in the order of 2 to 3 centimeters, making the antenna quite small compared to the wavelength, which is about 70 centimeters for 433 MHz. And because the loop is very small, it means that the antenna must be carefully matched with very low loss matching components. With the matched small loop antennas, there is an interesting but as such an undesirable feature. It magnifies the small changes in the antenna impedance due to the environmental factors. And this is actually in the heart of our topic, how to get this in control and how to minimize this. And what is so special with small loop antennas then? So from the antenna design and matching perspective, the biggest problem is that the radiation resistance is very small. It is in the order of only 50 milliohms. And alone, the bulk AC resistivity of the loop may be many times higher, typically about half an ohm. And because we have so low radiation resistance, it emphasizes the importance of selection of very low loss components and the loss control otherwise in the application. And it turns out that a loop antenna's performance is best characterized by the current that flows in the loop, rather than looking so much of the reflection coefficient at the source. And obviously S11 is an ingredient in the problem, but the loop current in itself is a much better figure of merit for loop antenna. And it's also worthwhile to notice that the layout implementation has much more role for small loop antennas than with big antennas at the same frequency. And again, the reason is that it is possible to end up with the design where almost all the power from the source is absorbed by the layout and no current flowing into the loop, and so no radiation. So if we compare a small dipole versus a small loop, a dipole antenna of comparable size has much higher radiation resistance, so we might ask why not to use that. And there is a good motivation for loop antenna, and that is that a small loop is essentially a magnetic dipole, and it is reasonably weakly sensitive to human body proximity. It is different with a dipole, which is highly dependent upon body proximity. So we carried out some numerical experiments using axiom and parametrizing the distance between 5 to 100 millimeters from the loop by a thick lossy slab. And that slab material approximates that of a hand with thickness 20 millimeter, dielectric constant 35, and loss tangent 0.52. And if we only look at the very reactive input impedance, we can't see really much change over distance in either case. It is quite different if we use an idealized matching circuit, kind of a microscope. And if we perform an ideal matching to free space and then apply the lossy slab, then we get these two graphs. So the loop reflection coefficient, it improves reasonably systematically when going from very close proximity towards free space, while that of the dipole reflection coefficient, it stays near the Smith chart edge. So the matching is not improving the same way. So let's look at the loop problem closer. So we have created a model, a mock-up model in Axiom of a remote access key antenna loop, and using dimensions that are somehow realistic, at least so 3 centimeters by 2 centimeters. So we have a PCB feed and matching area, and then the loop itself. The loop area is about 600 square millimeters, and using the given formula, its radiation resistance is indeed about 50 milliohms. And when analyzing this model, we are chasing very, very small details in the EM simulation. Therefore, it is important to use high accuracy settings and the direct solver in Axiom. And so with an EM simulation, it is very easy to separate the different losses. So we can simulate using an entirely lossless model, and we observe indeed 57 milliohms, which is in very good agreement with the theoretical expectation. And this now corresponds to the radiation resistance. There are absolutely no other losses present. And then we can add loss components one at a time and find out that the highest loss contribution comes from the loop metal itself. So this is in the design definitely one point to worry about, and maybe making the loop metal as wide as possible in order to minimize the kind of a straightforward bulk losses of the loop itself. So with a low loss material, the substrate losses is also relatively significant. The ground plane contributes some amount. But the overall conclusion is that the radiation efficiency of that antenna is only about 10%. And so this is the maximum we can even hope for. If we look at the matching problem from the classical perspective, then we seek a circuit that, if simulated or measured differential source impedance, then we have a differential load. And if we use Optenni Lab, we can read in Optenni Lab this one-port S-parameter file and find a matching circuit and make an interpretation as a differential circuit, as shown in the picture here. And if we consider a realistic implementation, then we use real library components, and now we have series capacitor, shunt capacitor as a design candidate, and as an example we use AVX AccuParts with tight tolerance, build the corresponding layout in Axiom and simulate that model. And the result is actually pretty good. And the model or the circuit that we get from Optenni Lab needs just a little bit tuning for capacitor C2, the shunt capacitor between the feed lines. So we will be looking at this circuit a little bit closer. There are two main factors that influence the design sensitivity and the stability. One is obviously the discrete component tolerances. And then, especially with small loop antennas, also the variation which is caused by manufacturing tolerance and the environment. The environment means the user hand primarily. The manufacturing tolerances are the main contributors are the variation in the substrate thickness and the dielectric constant. In the simulation domain, we can model the hand impact. If we use Axiom, very quick simulations, we can get a somehow representative model using this lossy slab as before. So it turns out to useful to look at both the differential and common mode reflection coefficient. And if we change the dielectric constant by -5%, then it turns out that the reflection coefficient phase changes by 0.23 degrees and the common mode reflection coefficient phase by about 1 degree. And the same way, we can repeat an analysis by changing the substrate thickness and find the changes in the phases. And also, if we introduce the slab model at, say, 10 millimeter distance, then we can record the changes in the differential and common mode phases. And now, because the changes have always the same sign for differential and common modes, we can define two corner cases, two extremes, due to the changes in the manufacturing tolerance, in other words, the dielectric constant variation and the substrate thickness. And we can also take the slab into account. So from the impedance perspective, the corner cases is the corner case 1 is the maximum dielectric constant, the minimum thickness with the slab present, and the other corner is then the minimum dielectric constant, the maximum substrate thickness characterized in free space. And it's an interesting fact, by the way, that if we compare the impedance sensitivity to dielectric constant and substrate thickness, it tends to dominate the impact over the slab presence. And this highlights the insensitivity of the magnetic loop to dielectric loading. And so the whole environmental variation range can thus be covered by only looking at these two corner cases and the nominal case in the middle. And so if we apply these corners to the design candidate, we get this result. So we have the magenta curve corresponds to the nominal values, then we have the brown curve for the second corner and the blue for the first corner. And the slab presence increases quite a lot the loop resistance due to the additional losses, and that's why the impedance trace is shrinked. And on top of these environmental variations, we have the component tolerances. And so if we sum them together and add component tolerances at a single frequency, in order to have a bit more clean graph, we find this result. So we can see the variation around the nominal values, around the second and first corners. And now we are using the most accurate components we can find from the libraries, so it's as such a reasonably sensitive design. And in the presence of the slab, the component tolerance contribution is pretty interestingly, it's quite small. And what all this does then mean from the loop current perspective? Because the loop current is eventually the current that is contributing to the radiation itself. And to model that, we added an internal port in the middle of the loop, and it serves as a current gauge. So we can excite the circuit with the matching circuit in place and then simply measure the current. And in microwave office we use the nonlinear measurement IComp. And we can see that with the nominal corner we have 61 milliamp current and then some variation due to the component tolerances. But the worst case with the slab model nearby, we have only 16 milliamps current. So we have a drop from 61 to 16, and this is a very significant drop. It is like more than 10 dB. So the overall random loss that cannot be controlled very much, maybe of the order of 10-11 decibels, the most of it coming from the environment. And so the main challenge is how to get this problem alleviated. In Optenni Lab we have a new novel tool called the Impedance configuration tool, and it allows us to import the corner cases and the nominal cases in one shot and find a matching circuit that compromises and balances the performance under the corner and nominal cases, such that the worst case performance is optimized. And so it may turn out that it is a good trade-off to decrease the nominal performance if the worst case corner performance is improving a lot. Because this exactly means reduction the dependency on environmental factors. And instead of just nominal S-parameter data, we also take the two corners. And so we build an axiom model of the loop with the layout present and the current gauge port also included. And we combine the feeding ports 1 and 2 as a single differential input. So the schematic is shown here. And so from Optenni Lab simulation perspective, the trick is to maximize the current at this current gauge port, which is defined as a very low ohmic port that is not influencing the current flow in the loop very much. And so we have the following setup. So we have the feed port, then we have the 10, in this case 10 milliohms current gauge port over here, and then we have 2 series and 1 shunt component over there. And feeding in the corners and the nominal case, we get this circuitry, which is a little asymmetric. The loop is not perfectly symmetric, so this is as expected. And now when we evaluate the currents in the current gauge port, we find out that the nominal performance is reduced from 61 milliamps to 38, but the worst case performance is much better. So it has improved over 4 decibels. And also the green and the blue corner cases are neatly in balance at 433 megahertz, so none of them is dominating. So the question now, what is the theoretical limit? So what is the maximum amount of current that we could expect? So we can calculate it from the total loop resistance quite easily. And so if we simulate the total loop resistance with the slab present, we can see that it's about 2.2 ohms. So for 0 dBm input power, the maximum current is about 30 milliamps. And so we reached the nominal, so not considering the component tolerance, with the nominal component values, we get very close 29.6 milliamps. It's almost suspiciously close to the theoretical limit. Having a little bit closer loop having a little bit closer look of the problem, we can distribute a number of current probes around the loop and average it's not entirely uniform, and find out that it's about 29 milliamps is the average current that we simulate. And does it then stack up? If we look the return loss, we see that about 15% is reflecting back, and in Optenni Lab we can analyze easily the component losses as percentage of available power, and they sum up to about 4% of the power, which means that there is about 0.81 milliwatt power which is delivered to the circuit. And this corresponds to 27 milliamps of power, and the current is actually pretty close to the say distributed average of the current that we see when using the current gauges. And so we can the conclusion is that the result really stacks up with the theoretical maximum, but also that there is not much space for improvement. So this is very close to the optimal that one can reach. And this means the other reduction in the performance then, which is due to the component tolerances, this is a factor that cannot be controlled by the design. It can only be controlled by the choice of the components. So to recap, we have mutually conflicting corners which determine the extreme cases with respect to which the performance should be optimized in a balanced way. And essentially the target is to maximize the envelope of the worst case current over the corners and over the component tolerances. And Optenni Lab's impedance configuration tool can be used quite straightforwardly. And indeed the corners, green and blue, are in good equilibrium. Looking at the measurement, from measurement perspective, with simulations we have lots of control how we define ports and so on. And so there are challenges in the measurement noise, so we can first have an unmatched VNA, use a theoretical matching circuit, and to control the measurement noise, say for example using the VNA's averaging filtering functions in order to find a kind of a stable standing point. And once a reasonably stable measurement setup is found, one can create the corners using the hand phantoms and then emulating the substrate tolerances. It may be difficult to find physical samples of PCB that represent the extreme corners, but fortunately we can emulate them. And we need the current gauge in the loop, and otherwise it may happen like shown in the picture here, that we may end up with a solution where very little current is flowing in the loop but very high hot current in the matching circuit region. So we need to carry out a 3-port measurement with ports at both ends of the loop, and then at the current gauge port, and then carry out 2 3-port measurements, free space and hand phantom. And then we can check what is the differential and common mode impedances in each case, and then emulating the changes due to the dielectric constant and substrate thickness. And that emulation or data perturbation can be done as follows. So in microwave office we can add a small transmission line to both inputs and optimize the electrical length and impedance of those transmission line segments such that we get the desired change in differential and common mode impedance. And in practice it would look something like this. So we have really small or short transmission lines, positive or negative length, but they are optimized, the parameters, such that they will be acting as like an impedance phase transformers in a controlled fashion. And now this new 3-port is now the emulated corner case that we plug in to the layout model. So we have measurement, the raw measurement, the perturbation, current gauge, and the layout model, and then component ports. And then we expose this in Optenni Lab, and in this case we have now 2 nominal datas. We have the 3-space case, the hand phantom, and then the 4 corners. Now entirely based on measurements. And so these 6 impedance datasets can then be fed into Optenni Lab's impedance configuration tool and to seek a balancing solution. And so we have repeated these steps using the, again, emulating now the measurement, so from a little bit different standpoint, using these perturbed 3-port models. And quite remarkably, we end up with exactly the same circuit than directly perturbing the dielectric constant and thickness. And so this confirms that we can extend the methodology from the simulation domain into measurement domain, which is then the actual problem anyway. So to conclude, we have explored a new way to characterize a very low ohmic antenna and presented a corner analysis-based methodology that provides as stable matched antenna as possible by maximizing the minimum performance over the corners. And the results that we get are nearly optimal, as confirmed by comparing with the theoretical limit. And in the example case, it is more than 4 decibels better, or 2.6 times higher radiated power compared with a classical reference design. So the whole point is to say, when we look at this, say, S21 figure of merit here, which is now the power coupled to the current gauge port, is to maximize this point over all the corner cases. And once reached, then we know that we have reached the optimum. I thank you for your attention.